Hello everyone, welcome to Graphing Rational Functions Day 2. Now yesterday we had our intro. We were working with parent functions and their transformations, all things that we had seen before in previous units. Now we're going to gain a little bit more freedom and work with functions that aren't really based off of parent functions. Now please have out that Rady foldable that we talked about today in class. That's going to be essential not only for these notes, but tackling all the problems for the next few days. Hold on to it, it's your lifeline. Okay, we're going to get started with the definition of a rational function. Now the official definition is there, so please pause the video now and copy that down for your notes. Okay, got it? Great. So what the definition is basically saying is that we're working with a fraction where we have a polynomial on top and a polynomial on the bottom. Now there's a note there about the domain, and we've talked about that in the previous couple of lessons, where we really have to watch out for where that denominator is 0. That's where our function is undefined and where we'll have restrictions on our domain. You'll see what that looks like on the graph today. Let's get straight into things with our first problem. Now with these, just as with adding, subtracting, multiplying, and dividing rational functions, our first step is going to be, yep, you guessed it, factoring. In this case, I can just factor the numerator by taking out the common factor of 4, leaving me an x minus 3, and in the numerator, we're fully factored, it's just x minus 1. Just a quick note, sometimes with Rady, it'll be easier to look at the factored form, but other times it'll be easier to go back to your original function. So when you're factoring, please make sure to keep your work neat so that you can still reference either of those forms. First up in Rady is r. R stands for roots, that's our x-intercept. And we solve for this by setting our numerator equal to 0 and solving for x. In this case, it looks like 4x minus 12 equals 0. Isolating x, we want to add 12 to both sides, leaving us 4x equals 12. Our 4 is multiplying with x, so we can divide that out on both sides, giving us x equals 3. Remember, x-intercept is where we're crossing the x-axis, and y is 0, so we can write this as a point, 3, 0. We can go over to our graph, and we know that our function is going to pass through the root on the graph at 3, 0, and it cannot cross the x-axis anywhere else. Important to note. Now, the next thing that we're going to look at is our A, T, and E. I've circled those because these all have to do with asymptotes. A starts us off by looking at our asymptotes vertical. That's going to be where we look at the domain restriction, we set the denominator equal to 0 this time, and solve. X minus 1 equals 0. Solving for x, we get that x equals 1. Now, we knew that there was only going to be one vertical asymptote because we look at the denominator and there's only one term here that gives us that possibility for our denominator to be 0. And it's true, we have one solution, x equals 1. We're going to go ahead and draw that vertical asymptote. I bring that up because it's going to be possible for us to have more than one vertical asymptote. We'll have some examples later on. Now that we've drawn our vertical asymptote, let's take a look at t. Our t has to do with two different things. That's what t stands for. Tangent over together. Tangent or togetherness. This is where we're looking at our terms in our function and seeing if we have any factors with multiplicities of 2. This could be a monomial to the degree 2, or a factor that's taken up to the degree of 2. In our case, we do not have any, and so we'll simply note that there's none. We'll not have a tangent or a togetherness. We'll see what that looks like once we've gathered some more information. Let's look at end behavior. End behavior, this is our horizontal asymptote. So our A dealt with vertical, E deals with horizontal. Here we're looking at the highest degree of our polynomial on top and the highest degree of the polynomial on the bottom. In this case, the degree is 1 for both of them. So we're dealing with the situation where it's the same. Then we look at y equals ab, stab. Same, then y equals a over b. Now what are a over b? That's those leading coefficients to our highest degree term. In this case, we have 4 and 1. So our end behavior will be y equals, a is our top one, 4 over 1 is our bottom, b. But 4 over 1 is just 4. So that means that at y equals 4, we have a horizontal asymptote. I'm going to go ahead and draw that in as a dotted line. The last piece of information in radii is y, the y-intercept. We find the y-intercept just as over here you set y equals to 0. Now it's when x equals to 0, when we're crossing this y-axis. So I go back to my original function, and wherever I see an x, I plug in a 0. Y equals 4 times 0 minus 12 over 0 minus 1. 4 times 0 is 0, minus 12, negative 12. 0 minus 1, negative 1. Simplifies down to just 12. So at y equals 12, I'm going to have the y-intercept. We also write this as a point. That's when x equals 0 and y equals 12. I go over to my graph, and 0, 12. I know my function is going to cross at that point. So we have 2 points that we know our function is going to pass for sure, and 2 asymptotes, one vertical and one horizontal. Now these asymptotes are going to serve sort of like magnets for our function. Let's start over here on this one. Now we know that we have to pass through here and that our function is going to be approaching but not quite touching these 2 asymptotes. Now we can use that information to kind of start over here, getting closer as we go away to the asymptote and cross at this point. The same kind of situation is going to happen at this point, and then we kind of just fill in along the middle. It'll look something like that. Okay, same idea over here. We have a point that we need to cross through and 2 sort of magnets with these asymptotes. That's what that's going to look like. Let's see if that makes sense with what we have for our t. We had none. That means we had no tangent, and it's true, we're not bouncing at this point, we're going straight through it. So good, no tangent. And we also didn't have togetherness, which holds up here as well, as on this side of our vertical asymptote we're going up, and over here we're going in the opposite direction, down. The last thing you may be asked with problems like this is about the domain and range. I've input that information for this graph right here, so please try it on your own, see if you get the correct answer. If you still have questions, let me know. For the rest of the problems in this video, what I'd like you to do is have your foldable out and fill out the radii information on your own. I will have it pre-filled into the video for you to check your answers, but please make sure you're really using this time to go through it alone. It's not going to help you just to copy down what I have. You need to get that practice so that you get faster and faster and you become more familiar with radii. The other thing I'd like for you to do is with the graph, use your R to fill out your x-intercepts, if any, your Y to fill out your y-intercepts, if any, and A and E to fill out vertical and horizontal asymptotes, respectively. What I'm going to focus on is then extracting more information about radii to tell exactly where our function is going to be, because we're going to visit a few different special cases. Okay, so at this time, pause the video and fill out your information for number 2. What I'd like to point out is that unlike our first problem, we have 2 x-intercepts in this case. And also, we have two vertical asymptotes. Remember I noted that we could have more than one. Now that comes from us having two things multiplying here in the denominator, so there's two chances for there being a 0 down there. Now the graphing part I really want to talk about, because you'll notice that on the far left and the far right we have these asymptotes, but unlike before we don't have a spot or a point anywhere on this graph that can indicate to us if it's going to be here or if our graph's going to hug the asymptotes down here. So that's okay. Sometimes you're going to have to do some test points. So what you can do is choose an x value on this side of your asymptote, plug it into your equation, and see if your y value ends up being on the top or on the bottom. Try to stick to easy numbers as much as you can. So when you test this point, you'll find that the y ends up being in this part of your graph. So that's all the information we need, just one point, and we can show it as this. Now we can go over to these 2 points. We know that we have to cross the x-axis at both of these. And since we didn't have any tangency or togetherness, we know that we're going to go through the x-axis at these points. That lets us know that we're going to end up having a parabola of some sort here. Now these still serve as magnets, and so because we also didn't have togetherness, we know that our graph is going to be going in the opposite direction on the other side of the asymptote. And so we're going to have a parabola. And try to be better about going through your points there. It looks like this. Again, because of the togetherness, over here we're going to be going in the opposite direction on the other side of the asymptote. And that's how we know that our graph continues up here. All right, so now take a chance to try to fill out number 3, and we'll see if you get a little better with practice, a little faster. Here's number 3. Things to notice here is that we do not have any roots. You'll notice also that we have that horizontal asymptote at y equals 0, and that explains why we have no roots. This time, I'd like to draw attention to t because we do have a multiplicity of 2. It's right here in the denominator where we have a factor that's being squared. Now, since it's on the bottom, that means that we're going to have togetherness. That's why I've circled that there. Also, we have a different situation for e here. In this case, we have a degree of 0 because I could have written x to the 0, which remember from our exponents unit is just 1. Here next to my 2, and that's my degree for the top. And in the bottom, of course, I have my squared here. I expanded it out so it'd be a little easier to see. So I have this 2. So it's bigger on bottom, so my y equals 0 is going to be my horizontal asymptote. All right, so we have this graph, and what we can do is start off where we have a point and use our asymptotes as magnets to draw what our graph will look like there. Next, we'll use t to say, yes, it will be together. So unlike what we've had in the first 2 problems, on this side of the asymptote, we want to be going in the same direction. Whoops, little hiccup there, but that's the general shape of this graph. All right, take a look at number 4, and then we'll talk about it. Okay, here's number 4. If I'm going into my explanation too fast, please feel free to be pausing the video as you go along. Things of notice here is that we have a new situation for t. We have a multiplicity of 2, but this time it's a monomial that's being squared, and it's on the top, so it means that we're going to have a tangent this time. For a graph, a good habit to have is to first look at the points that you have graphed and see if you have enough information to fill out that portion of your graph. Now here, this point, the thing that we know is that we have a tangent. So we're going to not go through the x-axis at this point. We're going to bounce back. That means we're either going to have a parabola that is opening upwards or a parabola that's opening downwards. Now, you may be tempted to say, well, we have a horizontal asymptote, so we cannot cross at this point. It must be a parabola that's going down. Now, that's not the case. Notice that it's really important that this was an E for end behavior. That means that the horizontal asymptote only affects our far left and our far right. You will have some cases where we end up actually crossing that horizontal asymptote in the middle of our graph, and that is okay. It is not okay for vertical asymptotes. Those will never be crossed. Horizontal asymptotes, that's where you're just looking at the ends. Okay, so we don't quite know enough whether to go up or down. So we have another situation where we need to do a test point here. Now with the test point, I can choose any x value that I'd like to, plug it in wherever I see x in my function, and solve for what y equals. In my case, I chose to look into when x equals 2, and I found that y equals negative 2/3 at that point. That means that our function is going to be going through this point. That gives us enough information to know that we are going to be coming from the bottom to be able to go through this point and touch that x-intercept. Now the fact that I have a tangent lets me know that when I reach this point, instead of going through the x-axis, I'm going to bounce back, and when I hug my asymptote, it's going to end up being a downward parabola looking like that. Okay, now how do I know what the function looks like on this side and on this side of my asymptotes? While I go to my together, I see that we do not have togetherness, so we're going to be going in the opposite direction on either side of the asymptote. Since here it was going down, here I start going up, and that's what my graph looks like. Take a moment now to look at radii for problem number 5 and graph your asymptotes and any x or y intercepts. For number 5, radii was pretty straightforward, and we've seen cases of everything that went on over here. The graph, though, is really important because it brings up something that I was just talking about in the previous problem, that our horizontal asymptote, we may be able to cross it in the middle of our graph, and here we have such a situation. So like I said, a good habit to have is look at your points. We see that one of them is actually on our horizontal asymptote right there, since our horizontal asymptote in this case is the x-axis, but we do have an x-intercept. So that tells us that we're for sure going to be crossing that horizontal asymptote. Now our point is on the top half, so we're going to have to cross this. Now since we cannot cross the x-axis at any other point where we do not have an x-intercept, we know that it has to be going this way to begin with, and then we'll go through our x-intercept and hug that other vertical asymptote. Because otherwise, what would have happened is if we had started on this side, we would have eventually had to cross the x-axis to pass through both these points that we know are on our graph, and we cannot do that because we can only pass through the graph where we have an x-intercept. Good to know. Since we have no togetherness, we know that this graph is going in this direction down here, and also will be opposite until our graph continues on this side. For our last problem, number 6, I would like you to come to class with radii filled out, and we'll talk about how to graph it in class tomorrow. Have a great night.